In this video, we're looking at another method for solving equations called the fixed point iteration method. You'll remember that we've been trying to solve the equation x cubed minus 7x minus 5 equals 0. Now, we did solve this entirely using the Newton-Raphson method, but we're going to just use it as a starting point for looking at this idea of the fixed point iteration. The graph for the function y equals x cubed minus 7x minus 5 looks like this. And on that graph, the solutions are the points at which the graph cuts the x-axis. And using Newton-Raphson in the previous video, we have found that the solutions are that x is equal to minus 2.166, or x is equal to minus 0.783, or x is equal to 2.949, all correct to 3 decimal places. Now, looking at the equation that we're trying to solve, we can do some rearranging of that equation. So x cubed minus 5 is equal to 7x. And if we then divide by 7, we get that x is equal to x cubed minus 5, all divided by 7. In doing this, we've created two separate functions. On the left, where we've just got x, we can draw a graph of the function y equals x. On the right, where we've got x cubed minus 5 all over 7, we can draw the graph of y equals x cubed minus 5 all over 7. And the two graphs that we get as a result are these. The graph of y equals x is shown in blue, and the graph of y equals x cubed minus 5 all over 7 is the curve shown in green. And these two graphs also intersect, and with the same x-coordinates as the solutions that we're looking for from our original graph above, as I've sought to show there. The three intersections on the bottom graph are the fixed points about which we're going to perform this fixed point iteration. And if we were to continue with this one, we would rewrite that last relationship in this way, that xn plus 1 is equal to xn cubed minus 5 all over 7. And just as we did with the Newton-Raphson, we would put a starting value in, cube it, subtract 5 and divide the result by 7 to give us our next best guess, and repeat the process until we find that we're close enough to a suggested solution. So let's summarize the steps in the method and then see its application in an example. What we're trying to do is to find solutions to the equation f of x is equal to 0. And the first thing that we need to do is to rearrange that original function so that on one side we have just an x, and on the other side we have some other function, g of x. Once we have that, we're going to use a starting value, x0. Now, this will probably be suggested by work that you've done prior to this, using the change of sign method, finding an interval in which a solution exists, and then you use that starting value x0 to generate x1, x2, x3, and so on, using the relationship xn plus 1 is equal to g of xn. And you continue to do that until it converges on what is suggested as a possible solution. All right, so here's the example that we're going to look at and apply those steps. we've got the equation x cubed minus 10x plus 1 is equal to 0. So f of x is x cubed minus 10x plus 1. We're told that there is a solution in the interval 0 to 1, and we're asked to use fixed point iteration to find the solution correct to 4 decimal places. So beginning with the equation that we're trying to solve, we've now got to rearrange it so that we've just got x on its own on one side. So we'll add 10x to both sides so that we get x cubed plus 1 is equal to 10x, and then dividing by 10 we get x cubed plus 1 over 10 is equal to x. So we have x on one side, and our g of x is x cubed plus 1 all over 10. That we can now rewrite as xn plus 1 is equal to xn cubed plus 1 over 10. Now, just before we begin with our starting value x0, let's have a little look at that graphically. So on that graph, in red I've plotted y is equal to x, and in green the right-hand function x cubed plus 1 all over 10. And where those two curves intersect is the point that we're trying to find with the x coordinate equal to the solution. Let's begin to use this iterative relationship then. First of all, we'll begin with a starting value of 0, so x0 is equal to 0. Remember, we're putting this into an iterative relationship, and so on your calculator, if you type in 0 and press equals, that places 0 on the answer button of your calculator. And now, in order to enter xn cubed plus 1 over 10, open up a fraction, and in the numerator press answer cubed plus 1, the down arrow to get into the denominator, type 10, and then press equals, and that will give you the first value x1. And every time you press equals after this, you'll get the next value in the sequence x2, x3, and so on. And when we put that into the relationship, we find that x1 is equal to 0.1. When we put it in again, we get x2 is equal to 0.1001. Now I've added an extra 0 because that was exact, and therefore just to go one further than the 4 decimal places, I've added that last 0. And then again, x3 is equal to 0.10010003. And all of this suggests that the correct solution to 4 decimal places is 0.1001. Let's think about this graphically now. We began with an x-coordinate of 0, and we put that x-coordinate of 0 into g of x, and that provided us with an answer, and any point along that red line y equals x, the y-coordinate is the same as the x-coordinate, and so here will be x1, which we then put into the g of x again, and that produces another coordinate x2, and you can see that we're getting progressively nearer to the correct solution. This is called a staircase diagram. If we now try it using a starting value of 1, so x0 is equal to 1, x1 is equal to 0.2, x2 0.1008 would have a 0 afterwards, x3 0.10010024, and then finally x4 0.10010003, which agrees with what we found before, that 0.1001 is the solution. And again, we can think about that graphically. We took 1 as our starting value and we put it into our g of x. That produced a new value of x that we put into g of x again, which provided another value, and so on all the way down till we found the solution. And you can see that that is converging a little more slowly on the final solution. And don't forget to do the change of sign test for the upper and lower bound to confirm that 0.1001 is indeed correct to 4 decimal places. In this example, we're given the equation sin x minus 2x plus 6 is equal to 0. And we're told that that has a root in the interval between 0 and 2 pi. That immediately reminds us that we need to be in radian mode as we try to solve this equation. We're asked to use an iterative relationship and find that root correct to 2 decimal places. So we begin with the equation, and we've got to get it into the situation where we've got x on its own on one side. So if I add 2x to both sides, I'll get sin x plus 6 is equal to 2x. Then I can divide by 2, so that x is equal to sin x plus 6 all over 2. So I've arrived at an x is equal to gx situation, so I can now turn that into an iterative formula by saying that xn plus 1 is equal to sin xn plus 6 all over 2. I'm choosing to use as my first value the value 0, because I'm told that it's in the interval from 0 to 2 pi. And now I've got to enter 0 on my calculator and press equals to put it on my answer button. And then I'm going to open up a fraction and type sin answer, close the bracket to get out of the sine function, plus 6 in the numerator, arrow down to go into the denominator and type 2, and then press equals, and I'll get my x1, which is 3. I then simply need to keep pressing equals and recording the results that I get. So x2, 3.0705, x3, 3.0354. Now that is immediately of interest to me, because I've gone up and then up again a little, and then I've come down. x4, 3.0529, and I've gone up again. x5, 3.0442, I've come down again. x6, 3.0485, 7, 3.0464. At this point, it looks as though 3.05 is correct to 2 decimal places, but because I've got this up and down, oscillating around a particular number, I do one more to be sure, and yes, all of that does suggest that 3.05 is the correct solution to 2 decimal places. What does this look like graphically? Well, here we see the graph first of all in red of y is equal to x, and then in green I've drawn the curve of sin x plus 6 all over 2, although you'll see that I've represented it in a slightly different way as a half x plus 3. I know that it crosses the y-axis at 3. It'll go up to 3.5 and down to 2.5 and be oscillating as a sine graph usually does. My starting value for x was 0, and taking that up to the function and then going across, and then from there I have to go up again to get to the function, and now I'm going to be going across and down and around, and I'm trying to exaggerate this so you begin to see that this goes around and around, and perhaps unsurprisingly this is known as a cobweb diagram. And now the only thing that remains to be done is to check the upper and lower bounds for 3.05 to be sure that there is a change of sign, which confirms that that solution is correct. So we've seen in this video how the fixed point iteration is set up by rearranging your initial equation into the form x is equal to gx, turning that into an iterative relationship, using a starting value and hoping that it will converge on a particular solution. In a final video, we'll be looking at the ways in which this fixed point iteration doesn't always work and the measures that we can take to overcome this.